Got it? All right, I'll begin. Heavenly Father, we thank you for this day. Again, Lord, thank you for these students. I just pray you guide them to make the right choices in their life as they plan their future here. Let's help them to persevere in the very many challenges that face them this semester, that they do their best, Lord, each day. For your glory, Lord. In your name I pray. Amen. Okay, so I hope you watched the videos. In these videos, what did I show you? I showed you many things, didn't I? Yeah, we learned how to create power series for various functions. We learned the geometric series tricks. We learned how to multiply series, how to divide series, how to integrate series, how to differentiate series, all kinds of calculations, right? So it's important that you watch those videos, but I'm going to try to recreate some of that content again here today, just to try to drive it in. There's a couple of major theorems we're basically using. Let me state those. So here's the theory we use. And so basically here it is. If f of x is equal to a sum, let's say n equals 0 to infinity of a sub n times x minus a. I'm tired of a. Let me use x naught here. X minus x naught to the n power. Then, all right, 1 and 2. Number 1, df dx, the derivative of f with respect to x, is equal to the sum n equals 1 to infinity of n times, n a sub n x minus x naught to the n minus 1 power. And also, the integral of f of x dx is equal to some constant plus the sum n equals 0 to infinity of a sub n over n plus 1 x to the n plus 1. Well, you could make that n equals 0 if you wanted to. Why don't we do that? I mean, why do we prefer not to do that? Is there a reason not to bother with 0 here? Right. If I plug in 0, it's just 0. So it's like, why bother? Now, let me just express 1 and 2 in the sort of more abbreviated fashion. So 1 saying that if you differentiate, say a0 plus a1 times x minus x naught plus a2 times x minus x naught squared plus da-da-da-da, right? Then how do you differentiate? Well, you differentiate term by term, right? So that's just a1 plus 2a2 times x minus x naught plus da-da-da-da. And so the derivative of this constant is just 0. 2, what it's saying is if I integrate a power series, I can do so term by term. So in other words, this is equal to some constant, because we're calculating an indefinite integral, right? And then plus a0 times, and then, okay, fine. So to be, oh man, come on. Really? That's no bueno. There. Sorry about that. Sometimes, I get x not equal to 0 on my brain. About 80% of the examples I'll do for you will set this x sub naught, the center point, to be 0. Right? That makes it what's called a Maclaurin series. Anyway, so if we integrate x minus x naught with respect to x, you can make a u equals x minus x naught substitution. You can think of it that way, right? And so then u squared over 2, well, that becomes Oh, I'm not there yet. This integrated just gives me x minus x naught, and then plus 1/2 a2 x minus, I'm an idiot. A1 x minus x naught squared plus 1/3 a2 x minus x naught cubed, and then so forth. So let me just kind of try to demystify what I'm saying here. All I'm saying is, if we have a power series, there are theorems which we can prove. I probably won't, but we could. I can't decide. Maybe we'll prove them. Anyway, it depends. Timing, amount of coughing I'm doing at that point, things like that. But these theorems are known, and I want you to use them, that we can differentiate and we can integrate power series term by term. Okay? Later we'll talk about the domain for a power series carefully. There's something called the interval of convergence. We're gonna explain that when you have a power series, it always either it converges on some finite interval, or it converges everywhere. And if it converges on a finite interval, it's either like you get both endpoints, or you get one endpoint and then the other on the left or the right, or you lose both of them. So you've got like 4 different possibilities in the finite interval case. Or sometimes there are power series which just converge at the center point. There's always at least one point of convergence for any power series. But anyway, I'm putting that discussion of the interval of convergence and radius of convergence off in here because I think it's healthy for us to first talk about how to calculate with power series until we're really good at it. Then we'll come back and we'll fuss about domains, all right? But I will tell you this, presenting a function like this, saying a function is written in terms of a series at each point. This is what's called a power series, all right? There's a well-known book of calculus from like 1780 or so by Lagrange, and Lagrange, when he starts the book, he says, consider a function. And then you know what he does, because people didn't think about rules between sets then, they thought about formulas. And so like the most general formula he could write for a function, arbitrarily so, was this. And so there was a time in calculus when we said function, we meant power series. And it's taken us a long time to sort of get more nuanced in that. But anyway, so you guys cool with this and this? It's good. Let me show you an application. How about if we have f of x equal to the natural log of, let's say, 1 plus x, maybe? All right. Other question? All right, so, I mean, I've talked some about interval of convergence because when we did the geometric series tricks, then the radius of convergence is kind of there. But okay, I'm going to stop talking about that. All right, so this, if I was to do Taylor's theorem directly, I could, right? And I could find the power series for this if I wanted to, centered at 0. But what I'm going to do is I'm going to show you a trick. So we calculate df dx, which is what? 1 over 1 plus x, right? The reason I do that is because now it's a geometric thing. Well, to be more specific, it's the thing to which a geometric series converges, right? It has the pattern a over 1 minus r, right? You can think of this as a over 1 minus r with what? So what's the, you have to see this, right? A equals 1, yeah, r equals minus x, right? So then by the geometric series result, applying it once for each x that's appropriate, we have the sum n equals 0 to infinity of, well, 1 times minus x to the n. Hope you don't mind that I'm using n now instead of k. It's just because I'm tired of writing k. My k's are hideous. My n's are so much prettier. Not a terribly sophisticated reason, but it's the actual reason. So I'm just sharing it with you. Anyway, so this, of course, is the sum n equals 0 to infinity minus 1 to the n, x to the n. This, my friends, is a power series. what I have in the step before is not a power series. It's not a power series until you have this format, right? You have to have, you know, like this, and then this is the coefficient. And this is, of course, this is a power function, right? Centered at x naught. So this is why it's a power series. It's a sum of power functions. All right, if you don't have a sum of power functions times coefficients, it's not a power series. This is not a power function. It's something else. Okay. But this is a Maclaurin series, so great. Now what? Well, that's not what we wanted. I mean, we found a power series for this thing, but what are we interested in? We're interested in log x. How do we get back? Integrate, right? So if we look at the integral of dx over 1 plus x, that should be equal to the natural log of 1 plus x, right? Which should, well, plus a constant, basically. Let's say plus c1, and that should be equal to, let's say, c2, right, plus the integral, plus the integral of that, right? Well, fine. The integral of the... Sorry, I'm having... internal struggles with how to organize the calculation. But there, I fixed it. Okay, so now we use the theorem, which says that this is equal to what? Like some constant, let's say c2, plus what? Plus the sum, n equals 0 to infinity, minus 1 to the n, over n plus 1, x to the n plus 1. Any questions? So I'm just integrating term by term. So you can rewrite this, right? What we really have is the natural log of 1 plus x is equal to some constant, right? Plus the sum, n equals 0 to infinity, minus 1 to the n, over n plus 1, x to the n plus 1. Now, is the log of 1 plus x arbitrary? Is there some kind of arbitrary constant in the formula for log of 1 plus x? You can tell from my tone the answer is no. How do you figure out the constant then? What do you know about natural log? Can you know anything specific about it? How about log of 1? What's that equal to? 0, right? Yeah, so if I put x equals to 0, that's nice, because then we get log of 1 is equal to a constant plus this series, right? I don't really need to do all this writing. I'm just doing it so you understand what's going on here. We're looking at 0 to the n plus 1 power. What is 0 to the n plus 1 power? I mean, if there was a constant term in here, right? If there was actually a constant term in the series, then you could get that constant term back, right? But this series starts at x. It goes like x, and then x squared, and then x cubed, and so forth, right? Because n equals 0 gives me n plus 1 of 0 plus 1, which is 1. My point is, when you plug in 0 into the series, you just get 0. So this whole goes away, and so we get log of 1 equals to c, so therefore c is equal to 0. And there you go. We have earned a power series then. The log of 1 plus x is equal to the sum, n equals 0 to infinity, minus 1 to the n over n plus 1, x to the n plus 1. Now, you could ask the question, for what x is this legitimate, right? It's not going to be true for all x. So let's trace back our steps here. First of all, when we found the power series for the derivative, where was that true for? We need the absolute value of r is less than 1, which is to say the absolute value of minus x is less than 1, which is, of course, to say that the absolute value of x is less than 1, aka x is an element of minus 1 to 1. Right? And that 1 is not included. Right? 1 gives you divergent geometric series. Minus 1 gives you a divergent geometric series by the nth term test here. But then we integrate that thing, right? And one of the things I should mention to you is that when you integrate a power series, the integral of the power series sometimes has a larger domain, a larger interval of convergence than the original power series. Right? They'll always have the same open interval of convergence, but sometimes the endpoints can get thrown in. I keep talking about this thing I'm not supposed to talk about. Sorry about that. But it's kind of relevant here from the comment I want to make, which is it turns out that this is cool for, this is legit for x an element of, as it turns out, -1 to 1 included. If you plug in -1, what do you get there? If you think about it. Well, on the one side, you get log of 0. That's kind of troubling. But more to the point, over here, this series does not converge at -1. Because if you plug in -1, you get -1 to the n times -1 to the n. This is the harmonic series when we plug in -1. But when we plug in x equals to 1, this is the alternating harmonic series. Right? So if we look at the natural log of 1 plus 1, that's equal to the sum n equals 0 to infinity -1 to the n over n plus 1 times 1 to the n plus 1. All right. Now, if it's okay with you guys, I'd like to erase this. Can I erase that? You see why? Right. So you see what this is. This is equal to 1 minus a half plus a third minus a fourth and so forth and so on. This calculation is how I knew that the alternating harmonic series converged to the natural log of 2. All right, there's a little bit of analysis I'm cheating on here, but this is a pretty good plausibility argument as to why it has to converge to log 2. Es bueno? So this is an example of a geometric series trick. What a geometric series trick is when the thing another example of the same sort would be f of x equal to, like, inverse tangent, right? I'll go through this one a little bit faster. If I look at that, then df dx is what? 1 over 1 plus x squared, right? Which is equal to the sum n equals 0 to infinity of minus x squared to the n, which is equal to the sum n equals 0 to infinity minus 1 to the n times x to the 2n. So no, inverse tangent I can't find. It's not geometric. I can't use the geometric series result on directly, right? But if I differentiate it, I get 1 over 1 plus x squared. That is the right pattern for a geometric series. And so then I can then work my way back. I can say, aha, well then f of x is equal to some constant plus the integral, right, of this series. Which, if I had been just a little bit more bold, I would have skipped this step I just wrote. Once you understand what you're doing, you can just write this next one down. Inverse tangent of x is equal to a constant plus the sum of what? Sum n equals 0 to infinity minus 1 to the n divided by 2n plus 1, x to the 2n plus 1. Right, but inverse tangent of 0 is equal to 0 implies that the constant is equal to 0 as well, because again we have a series which doesn't have a constant term. So when you plug in 0 into that series, it's 0 as well. So there you go. There's the power series for inverse tangent. Again, sorry if I know I'm in reruns a little bit because I did some of these things on the video, but I think if you see them twice, it's probably not a bad thing. All right. So there's the power series for inverse tangent. What's the first three terms in the inverse, in the this guy? Let's see here. So we start at what? N equals 0 gives me x. How about n equals 1? Minus 1/3 x cubed, right? How about n equals to 2? X to the 5th, right. All right, so, a major task we have is how do you actually construct the power series representation of a given function? Again, you might say, but you already told me Taylor's theorem, and that says I just differentiate and keep differentiating and put it together, right? That always works. Yeah, it always works, except can you calculate derivatives without end and find this pattern efficiently? What happens when you keep differentiating 1 over 1 plus x squared? You get quotient rule after quotient rule after quotient rule. It's quite awful. With relatively little effort, we have found the complete power series expansion for inverse tangent because we used the powerful truth of the geometric series and a little bit of cleverness. All right, so this is a very important technique I'm showing you. It allows you to find power series for things without suffering the indignity of actually applying Taylor's theorem directly. That said, there are some things that Taylor's theorem is just how we do it. All right? Before I get to that, though, let me just pause here and ask if there are any questions. Yep.
I have a question that I would like to resolve. Would you be able to?
Well, it depends on what kind of question it is. What's your question?
So, finding the second order power series.
Find the second order power series.
What you were doing on the something to this, something like that.
Oh, 1 over 1 minus x cubed? Yeah, that I could do. He wants me to find the power series for this one, and I will do that. All right. Okay, so let's see here. So this, now that's not geometric yet, right? But what happens when we integrate? The integral of f of x is what? Right? What happens if we integrate 2 times? Well, let me just give this a name. Let me call this g. Let's say, what's the integral of g of x dx? I guess I have to deal with that too, right? There's a reason it doesn't matter, but technically, let me call this C1, and here's C2, C1 again, plus C2. Every time I integrate, I get a constant integration, right? Oh, hey, but the last thing I wrote is pretty, this is nice, right? Because now I'm to something that I can apply the geometric series to. So this is really just 1/2 the sum x to the n equals 0 to infinity, all right? Plus c1x plus c2, just leave those out there. So to get, let me just kind of diagrammatically show you what we're doing. We integrated to get from there to there, and then this we integrated again. So to undo that, all right, what I'm going to do now is I'm going to differentiate. Okay? And so g of x, all right, is going to be the derivative of the integral of g of x dx, right? But I'm going to differentiate the power series. Now, already the c2 is gone, right? c2 is gone. Derivative of c2 is 0. So this is gone. If I hadn't added it in the first place, it wouldn't have got us into trouble, would it? But on the other hand, we have 1/2 the sum n equals 1 to infinity n times x to the n minus 1. All right, plus c1. My heart is not in writing that c1 because I know it's just going to die in the next step. Right? So we're not back to f of x yet, are we? But notice that if I do this again, think about, I integrated 2 times to get to the thing which was geometric. Now I'm going to differentiate 2 times to get back to the thing which we started with, using the fact that integration and differentiation in this sense are inverse processes. So f of x, right, is equal to the derivative with respect to x of the integral of f of x, which is what we call g of x, isn't it? Yeah. And so then I just differentiate using term-by-term differentiation this over here. And if you don't mind, I'm just going to write down the answer, which is 1/2 the sum n equals 2 to infinity of n times n minus 1 times x to the n minus 2, and the c1 differentiated to 0. So there you have it. This is the power series. Well, I'll tell you one more step. I'll bring the 2 inside. So that's the sum n equals 2 to infinity of n times n minus 1 over 2, x to the power n minus 2. This is the power series for 1 over 1 minus x quantity cubed. Now, this is one of those rare problems, all right, where I would probably agree it's not much harder to use Taylor's theorem and find a pattern. All right? I would agree that Taylor's theorem here is a reasonable tool for this problem. Let me show you why. So here's the Taylor theorem solution to this. First of all, f prime of x is what? See what it is? It's minus 3 over x over, oh goodness gracious. Tell you what, let me fix this to start with and write f of x is equal to minus 1 over x minus 1 cubed. That's just going to be easier for me to think about if you don't mind. Okay? So if I have a minus inside a cube, I can pull it out, right? So differentiate this, I get what? I get minus 1 times minus 3, x minus 1 to the what? The fourth, right? So therefore, f prime of 1 is equal to what? Oh, goodness gracious, 1. Whoa, whoa. Oh, why am I... Why? Why would you plug in 1? I'm a moron. That's like absolutely the one worst possible point you could pick. Like anything except for 1 would be reasonable to try here. I have chosen the one point in the whole real line I cannot use. Yes, 0. I'm looking for the Maclaurin expansion. All right. The significance of these coefficients here by Taylor's theorem is that these actually are the nth derivatives at 0 over n factorial, okay? So if I calculate the derivatives, I can put that together. Like now, this thing we're doing right now, you have to imagine that we didn't do this. We don't already know what's in the box. All right, I'm showing you how to recover it from Taylor's theorem. Anyway, f prime of 0 is just, what did you tell me? 3. Yeah, 3. And how about f prime prime? So we get 3 times minus 4 over x minus 1 to the fifth, right? Therefore, f prime prime of 0 is equal to minus 4 times 3, right? What happens when you differentiate a 3 times? Right. So the third derivative, the third derivative, did I make a mistake in the previous one?
Well, it would just equal, well, it's negative 4 times 3 over negative 1, so it's just 12 and 14.
Oh, I forgot my minus 1 to the fifth, you're telling me. Yeah, thank you. That's good, because this isn't alternating. Oh, wait a minute, we don't know this. Let's see here. So this is 5 times 4 times 3, right? So I would point out that you can start to see the pattern here. The pattern is that this is equal to, 3 factorial divided by 2. This is equal to 4 factorial divided by, what was it? 2? Oh, that may be quirky. What is this? This is, oh wait, I guess it's not. 5 factorial divided by 2. Yeah. So I think you can see the pattern. I'm going to jump to the pattern. The nth derivative at 0 is going to be equal to, it's going to be equal to n plus 2 times n plus 1 times 3, right? Which we can rewrite as n plus 2 factorial, right, divided by 2. Because it's almost n plus 2 factorial, it's just missing the 2 at the bottom. So therefore, if you calculate fn, evaluated at 0 over n factorial, what do you get? You get n plus 2 factorial divided by 2 times n factorial, which, by the way, is n plus 2 times n plus 1 times n factorial divided by 2 times n factorial. The n factorials cancel, and you've got n plus 2 times n plus 1 over 2. Let me complete the thought here. So we found the derivative of the function as many times as you like. We evaluated at 0. This tells us how to construct the Taylor series for the function. What is the Taylor series for the function? Well, so what we have then is that f of x, which is 1 over, well, I said minus 1, right? Minus 1 over x minus 1 cubed is equal to the sum, n equals 0 to infinity, of this thing, n plus 2 times n plus 1 over 2 times x to the n. Now, you're like, if you're paying attention here, we use 2 different calculational methods, right? And we got 2 different answers. Is this troubling to you? Or do you accept my claim that these are different answers? They just look different. Why are these the same answer? Why is what I have in the box here, n times n minus 1 over 2 x to the n minus 2, equivalent to what I have up there, n plus 2 times n plus 1 over 2, n equals 0 to n. Tell you what, let me make a substitution and show you explicitly why they're the same. So if I let j equal to, let's say, n minus 2, then, in other words, n is equal to j plus 2. When n equals 0, oh, I can't do that. I did it the wrong way. I think n plus 2? Yeah, j equals n plus 2. I'm sorry, I'll get it right eventually. If j equals n plus 2, then what's that say? That says n equals 0 gives me what? j equals to 0 plus 2, which is 2, make this substitution, and let's see here, I get n is equal to j minus 2, right? So n plus 1 is equal to j minus 1, n plus 2 is equal to j, right? And so with that substitution, our series looks like sum j equals to 2 to infinity, n plus 1, n plus 2 is j, n plus 1 is j minus 1, 2 is 2, and you have x to the power not n, but j minus 2. And so you can look at this, and you can look at what we got down here, and you can see that it's the same exact pattern. It's just instead of using n, I'm using j. Right? And you could change the last j I have to an n, and you get the same sum. They're the same thing. So which is easier? Geometric series trick or the direct differentiation here? What do you think? Geometric thing? Yeah, I don't know. I don't have a strong opinion here, one or the other. I mean, this is a slightly complicated problem any way you slice it. I think the easier answer is this is a binomial series with k equals to minus 3, and that's the binomial coefficient. So, yeah. Hee hee hee.
I think there's like less thought
in the geometric series way of doing it, less thought there. Yeah. Yeah, I think I want you guys to get really good at geometric series, so do spend time thinking about those. But I also need you to know your basic standard examples of power series, so let's get back to that. I'm glad there was a question. If there wasn't, I was going to take a minute to smell the roses here, so to speak, which is just to point out, like, once you have a power series expansion for the function, you can integrate it, right? How do you integrate the function once you have a power series expansion for it? You just integrate the power series term by term, right? So if you can find a power series expansion for the function, you can integrate it. Everything we couldn't integrate before, we can integrate now. What's the rub? The answer is a power series, right? So if that doesn't constitute quote-unquote an answer for you, then I guess you're still sad. But let's not be sad. All right. So standard examples. I think I've already derived for you that the power series of the exponential is 1 plus x plus 1/2 x squared plus dot 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 dot, right? In other words, it's the sum n equals 0 to infinity of x to the power n over n factorial. So check this out. We know that e to the x is equal to cosh x plus sinh x, right? So this is the even piece. This is the odd piece of the exponential. Fun fact for you. The power series, the Maclaurin series, all right, to be more specific, the Maclaurin series of an odd function has only non-trivial odd terms in the power series expansion. The Maclaurin series for an even function has only non-trivial terms, even power terms. So to get the power series for cosh and sinh here, all you have to do is take the exponential series and split the even terms and odd terms apart. It's literally just that. So we have cosh of x is equal to 1 plus 1/2 x squared plus 1 over 4 factorial x to the 4th plus dot 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 dot. Whereas sinh x is equal to x plus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th and so forth. If you add these two series together, you get all the terms in the original exponential series. It's just taking the exponential series and splitting it into two pieces, even in odd terms. Excuse me. Okay, so where was I? let's write a formula for this that's a little bit slicker. A nice formula for just even terms is this. This is the sum j equals 0 to infinity, x to the 2j divided by 2j parentheses factorial. The sinh is the sum j equals 0 to infinity, x to the power 2j plus 1 divided by 2j plus 1 parentheses factorial. Those are the complete Maclaurin expansions for cosh and sinh. We can derive those from Taylor's theorem pretty fast. Like what happens if you... Well, let me not. I mean, I could do that, I guess. Want me to do that? I'd rather not. Let me show you a different way of thinking about it. So how to derive those. I'll show you the cosh x series from a sort of an interesting way. Cosh x is what? It's 1/2 e to the x plus e to the minus x, right? So that's 1/2. And we got what? We got the sum n equals 0 to infinity, x to the power n over n factorial, and then plus the sum n equals 0 to infinity, minus x to the power n over n factorial. So something I should point out here, guys, something that's even more important than what I've written is to understand the substitution principle, which is that I can replace x to u and get, like, e to the u is the sum n equals 0 to infinity u to the n over n factorial, right? So like here, I made a u equal minus x substitution to get the power series for e to the minus x. Substitution's a powerful principle. And so doing that, what happens to minus x to the n? How does that work out, algebra? Notice, so I can basically do a little bit of algebra here. Sum n equals 0 to infinity, and I've got 1 over n factorial plus minus 1 to the n over n factorial, parentheses, x to the n. If you don't mind, I'm running out of board space here, so I kind of skipped a step. But the extra step, I would have said, minus x to the n was equal to minus 1 to the n times x to the n. And then because I have x to the n on both things, I can combine the sums. Since they have the same starting point, I can combine the sums. But what's the deal with this? How's that work out? This is 0 if what? If n is odd, that's 0, right? Minus 1 to an odd power is minus 1. So you get 1 minus 1. They're both over n factorial, so, they cancel if n is odd. And what happens if they're even? It's 2 over n factorial if n is even. So I can replace this by the sum n equals to 2j, 0 to infinity, x to the n over n factorial. Or writing it in a less weird way, that's the sum j equals 0 to infinity, x to the 2j over 2j factorial. Or you can differentiate cosh and plug in 0, whatever floats your boat. A similar calculation with a minus in the middle makes this cancel when it's odd and makes it not cancel when it's odd and cancel when it's even, and you get the sinh series from that, just the same. Let me do something here a little bit based on this. So if I want to find Maclaurin expansion of, let's say, f of x equal to x cubed cosh of x squared, right, how would you do that? Do what?
Buy a new notebook.
Oh.
2 pages long.
Buy a new notebook. No. That's the thing is, actually, this is a very easy problem. Now, it is not an easy problem if you decide, oh, well, I know Taylor's theorem. What's Taylor's theorem tell us? It says f of x is equal to f of 0 plus f prime of 0 times x plus 1/2 f prime prime of 0 times x squared, right? So I just need to just keep differentiating it until I see the pattern. No. Incorrect. Wrong way to do this problem. Very wrong. There, I think I've communicated my feeling. All right. What you do is substitution paired with multiplication. So f of x is equal to x cubed times the, let's say, cosh of u. All right? What is cosh of u? It is the sum, j equals 0 to infinity, of u to the power 2j over 2j factorial. We just worked that out, although I had an x there, and now I'm putting a u there, but it's the same pattern. And then, okay. So what do I got? I've got x cubed times the sum, j equals 0 to infinity, of x squared parentheses to the 2j divided by 2j factorial, right? Which is x cubed times the sum, j equals 0 to infinity, x to the 4j divided by 2j factorial, which, one more finishing blow here, sum j equals 0 to infinity of 1 over 2 quantity 2 to the j factorial, 1 over 2j factorial, x to the 4j plus 3. That is how you do it. I didn't have to think too hard to do this, really. The hard thinking, in some sense, is, finding this to start with. So you need to learn the power series expansion of the exponential, the cosh, the sinh, the sine, and the cosine. With these 5 basic examples, we can build tons of other stuff, all right? Of course, there are also like second-order examples like inverse tangent, or the log of 1 plus x, or things like 1 over 1 plus x quantity cubed like we looked at a second ago. But the examples built with exponential, cosh, sinh, sine, and cosine, I view these as sort of the entry-level examples. The easiest entry-level examples, and so here it is. If you want the first 3 terms, what is it? J equals 0, x cubed, right? What's the next one? Honestly, I don't like to think about this as a way to get the first 3 terms. I like to think of it this way. What are the first 3 terms in cosh? 1 plus u squared over 2, right, plus u to the 4th over 24. 24 is 4 factorial. So that's x to the 8th, yeah? So it looks to me like the first 3 terms are x cubed plus 1/2 x to the 7th plus 1 over 24 x to the 11th, and so forth. Of course, you could plug into that formula and find the same thing, right? Like j equals 1 gives me 7 divided by the 2 factorial, which is 2. J equals to 2 gives me 8 plus 3, which is 11. 2 times 2 is 4. 4 factorial is 24. Look, guys, I can answer all kinds of interesting questions about the function just from this power series. Like, if you ask me, what's the second derivative of f at 0? Can you tell me what it is? The second derivative of f at 0. It's what? What did I hear?
Oh, 1/2.
Yeah, this is also equal to f of 0, right? Plus f prime of 0 times x plus 1/2 f prime prime of 0 times x squared, and so forth and so on, right? Where's the x squared term here? You have to use your imagination. There's a 0 times x squared in here, right? So you can equate the coefficients, and in fact, yeah, the second derivative is just 0. On the other hand, the third derivative happens to be 6. The seventh derivative, I don't know. I know that 1/2 is equal to the seventh derivative at 0 divided by 7 factorial, so I guess I know that the seventh derivative at 0 is 1/2 of 7 factorial. So if you understand and exploit Taylor's theorem, you can do all kinds of interesting differentiation questions. Anyway, I'll try to give you a quiz focusing on the geometric series technique tomorrow, okay? Thanks, guys.